Alright everybody, so today what I'm going to talk to you about is the last part of the intramolecular bonding. That includes ionic, covalent, covalent polar, covalent nonpolar. And so I have this this slide from before up on the screen, and this shows what we've done so far: resonance, formal charge, shapes, bond angles, molecular polarity. Today we need to finish this off with hybridization. And we need to finish this off with something called sigma and pi bonds. So let's get to it. So if I just skip ahead here to the hybridization part. So when elements bond and they form a compound, there's some changes that take place. We know that bonds are broken, and we know that new bonds are formed. But there's also some changes to the orbitals. So the orbitals start off where they are atomic orbitals, and then as they bond, they form something called molecular orbitals. Now, the orbitals will mix. They'll mix, and they'll also change shape and change the amount of energy that they have. And this process of mixing and overlapping is considered what's known as hybridization. And so when we hybridize, this will account for the shape of the new orbitals and accounts for the lower energy of the new orbitals. And that's really what we're trying to do, is we're trying to account for the shapes that we see in these molecules. So, talk about what a hybrid orbital looks like and what the process is that happens when things hybridize. So, what we have here is, if we were to take an example like CH4, how would that actually work? Well, if I take my carbon and I look at it before it bonds, the carbon has valence electrons 2s2 and 2p2. And when I look at these, I have my 2 electrons here, and in the p I have my 2 electrons here. Remember what an s orbital looks like. It has this spherical shape, and the p orbitals have this lobe shape. Now, somehow or other, when CH4 forms, the carbon in the middle now has 4 bonds, and we know the shape of this, hopefully you've memorized the chart, as being tetrahedral. Tetrahedral, where all of the orbitals that form are at this 109-degree angle that we have here. So they're at this 109-degree angle between them. The issue is that when we look at the p orbitals and the s orbitals, they're not at 109 degrees. Something happens to these orbitals. Something happens where they mix together and they form new orbitals, orbitals that are now at 109 degrees. Well, let's look. This carbon here, it needs to form 4 bonds. It has 4 domains. It's tetrahedral. So how does it do that? Well, what happens is the 4 orbitals, the 2s and the 3 2p, all mix together. What we form is 4 new orbitals. 1, 2, 3, 4. Well, I used a single s orbital, and I used my 3 p orbitals, so that gives me 4 new orbitals, and those orbitals are called sp3. Now, I know that this is confusing because up till now, we've talked about how when you have this number up here, it's the number of electrons. But now, these numbers up here are the numbers of orbitals, 1s and 3p orbitals. Now, we had 4 electrons. Those 4 electrons, 1, 2, 3, 4, each occupy a separate orbital. These sp3 orbitals, they have the same shape, and the shape that they have are these weird lobe shapes like this, these lopsided lobe shapes. And there's 4 identical ones of them. So here they are. And I'm going to paste them all in. So I have 4 of the same orbitals. Now the textbook does a much nicer job. You can see on the left here, we have our s orbital, then our p orbitals, And they are, as such, they hybridize and they form 4 sp3 hybrid orbitals. They show them nicely there. Look at what happens when these 4 orbitals all come together. They form this beautiful tetrahedron. The tetrahedral shape comes from the hybridization, the mixing of the atomic orbitals to form the molecular orbitals that we see here. Now look, you don't have to know this process. I'll tell you what you need to know in a second. But I just wanted to go through this with you to show you where the hybridization comes from and what it means. What do you really need to know? What you need to know is that there is different hybridizations, and I have them down here. sp is when you're linear. That means that you've mixed together 2 different orbitals. And I show that here. If we had 1 orbital and 1 orbital, they would look like this. If you are trigonal planar in that geometry, then you will have 3 hybrid orbitals. That'll look like this. And if you're sp3, you will have a tetrahedral molecule or trigonal pyramidal. Or you could be the bent with the 2 and 2 up in the chart, and then that one will be like this. And that's tetrahedral. So what you need to know about the hybridization is this is the shape, and this shape corresponds to this hybridization. That's what you really need to know. Now, there's something called sigma and pi bonds. And sigma and pi bonds refer to how the orbitals overlap with one another. If you are a sigma bond, then the orbitals, that did not work, then the orbitals, grab this, still not working, so I'm on eraser, the orbitals have an end-to-end overlap. So what does that look like? Well, what that looks like is, here's my NH3, and they show it with the orbitals. Each one of these in here, if we zoom in, are sp3. These over here are the hydrogen's s orbitals in blue. This overlap right here that I'm going to shade in red is an end-to-end overlap. And this is called a sigma bond. So in this case, there would be 3 sigma bonds. Now, in general, what you should know is that sigma bonds are always there when you have a single bond. What does a pi bond look like? Well, a pi bond is where you have a side-to-side overlap. So pi bonds occur when you have double and triple bonds. The pi bonds come from having a p orbital that will overlap with another p orbital side to side. And let me just show you that really quick here. This is what a pi bond looks like. They show you what it looks like, by itself if you had 2 p orbitals side to side overlap. But then this here shows you what it looks like if you have a molecule of C2H4. C2H4 looks like this. You have this double bond. So with this double bond, one of these bonds here is a pi bond. So here's my carbon, and then it has sp2, 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 sp2. But it also has, and that accounts for all of these bonds that I'll highlight here. 1, 2, 3, 4, 5. So those 5 bonds, those are 5 sigma bonds. But then it has the double bond, and the double bond is right here. And that double bond is happening based on the p p orbitals that are right here. And what happens is these electrons that are in the p orbitals that are not hybridized, they will overlap side to side. It looks almost like the letter pi. Now, this means that there's one pi bond. And I show you the same molecule down here, C2H4, all labeled up. These p orbitals that are up here, they have this side-to-side overlap. It could be above or it could be below. Now, what's the general rule for this? Here they show you. I show you again with all this stuff. The general rule for the sigma and pi is as follows. If you have a single bond, you are considered a sigma bond. If you have a double bond, you have a sigma bond and a pi bond. And if you have a triple bond, which I'll show you below, you have a sigma bond and you have two pi bonds. What does the sigma bond look like with a triple bond? This is a molecule of C2H2. And what you can see, the way that they did this was they have p orbitals that are overlapping in front and above and below and in back as well. So what you'll be asked is a question like this. I'll give you a molecule and I'll say, well, you have something like this. And there's all H's coming off here, and I'll ask you, well, which one is, how many sigma and pi bonds are there? And so then you can go through and count. Sigma 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 sigma. And then I can go through and with my other highlighter here, I can say 1 pi. And that's the question that you're asked. That's all that you're asked. Now, just to talk to you about hybridization, just so that you can see what it looks like, if I go back to the images up here, the hybridization, it occurs with the shapes. So if you're linear, you're SP hybridized. If you're any of these trigonal planars, either trigonal planar or bent, you're SP2. If you are tetrahedral, trigonal, pyramidal, or the other bent, you're always SP3. You can add up the domains and they'll add up to the number of hybrid orbitals. 4 will give you SP3, S, P, P2, P3, that's 4. Same thing over here, SP2 has 3, S, P1, P2. I'm not going to do the 5 and 6 domains, but maybe we can talk about in class what's going on with those. Alright, there's one more thing that I quickly want to touch with you, and that is about bond energies. And so the thing with bond strengths and bond energies, they refer to two important things. One is when we look at a single bond versus a double bond versus a triple bond. This bond here, the single bond, is the weakest, whereas the triple is the strongest. And this is in the middle. The single bond, as I mentioned in class, this is the longest, and this is the shortest. So you should know those rules. And if I show you some bond energies on this page here really quick, we have single, double, triple, it's getting shorter. Single, double, triple, getting shorter. If we put in the strength, this would be weakest, up to here would be strongest. Weakest to strongest. And you can see that for these different bonds, how the strength increases and how the length decreases. Okay, so I'm going to stop here. There are some flow charts for you to check out and look at. Those are really interesting. They give a nice summary. We'll talk about those in class. And then when we come back from Thanksgiving, we'll do the part of the chapter that relates to intermolecular forces. All right, thanks so much.